if you remember on Tuesday, we just became introduced into just this world of chemistry that you guys are kind of bemoaning about a moment ago. And we just introduced it very briefly. We talked about, we gave a brief definition to an atom and an element, and now we need to define what a compound is. So I think actually we did cover a compound. What did we define a compound as?
Mixture of multiple elements.
A mixture, very good. A mixture of multiple types of elements. And we gave some examples as well. Ones that you're going to be most familiar with would be water. Like anybody can say H2O means water, right? That means it's a compound of two hydrogen and a single oxygen atom making up this compound. Any questions about what a compound is? That makes sense. Okay. And so a compound is going to have unique characteristics from the individual element. Okay, so for example, oxygen will have certain properties by itself. Hydrogen has its own properties by itself. But when you mix hydrogen and oxygen together, we now have new unique properties. So water is going to have its own bonding abilities and interactive types of properties. So it's going to be a new compound. It's going to be a different type of reaction, reactive ability. Good example, we gave our elements like sodium and chlorine. We can see them individually, but we form a compound with them, and we form something that you've heard of before called sodium chloride. That's another one that you're probably familiar with, which is what? Salt, right? Your table salts. Okay? And so your table salt clearly has a completely different chemical property than its individual elemental form. Does that make sense? It's completely different. You would rather shake this on your steak, right, than the chlorine, or right, whatever this is, the sodium, well, plain sodium. To understand how these compounds and elements work, we really need to understand atomic structure. And did we already define an atom? A little bit. To define an atom, right, it's the smallest component of an element that still remains or contains those elemental properties. So they're kind of the single components of an element. Okay, so if I'm looking at the sodium element, I could look at a single tiny submicroscopic particle called an atom. Follow along with that. If we look at an atom, we're going to look at its very kind of basic structure. Are we okay to move on? We'll come back. Let me help you. Okay, if we look at the structure of an atom, there are some components that make up an atom. Okay? So I'm on page 2 of your chapter 2 handout. If we look at the components of an atom, the 3 primary regions that we'll study include what are called neutrons, protons, and electrons. Okay, protons, neutrons, and electrons. These are particles that you can't visualize them. That's why it kind of gets a little bit difficult. We do have some technology that is changing, that we're able to see some structure of some atoms, but you can't see it without a microscope, a really high-powered, unique microscope. But if we look at the components of an atom, within an atom's nucleus, you'll find 2 things. I have it listed first, protons and then neutrons. But I'd like for you to note, maybe on the far margin, that these protons and neutrons are found in what's called the nucleus of the atom. Nucleus is just a term to describe the center. We're going to use the nucleus later to describe the center of a cell structure, right? You could talk about the nucleus of the mosh pit at the concert that you go to, right? The center of something. And so the center of the atom, the nucleus of the atom, contains two components called protons and neutrons. By definition, that kind of gives some description of what they do, or some properties about them. What do you think about protons? They have a positive charge. Protons are going to contribute a positive charge to an atom. Neutrons must be neutral. Neutrons are electrically neutral. So the protons and the neutrons are found in the atomic nucleus. Neutrons are electrically neutral. Protons are electrically positive. So what do we probably need also to make sure this thing is balanced? And something negatively charged, and those are called electrons. The electrons are negatively charged. They are not found in the nucleus. They're found in what's called the orbit. They orbit. That word, okay, orbit? They orbit the atomic nucleus. So protons give positive charge, neutrons give a neutral, they're not charged, and our electrons are negatively charged. From this standpoint, we're going to go into a little better detail about the nuclear components of an atom, but the rest of the class is really going to focus on those reactive electrons. So we've got to see how they work. Right, so as I mentioned, the electrons are out in the outer orbits. So the question is, how many, how much, etc. And so each element is going to have a unique atomic number. And that is indicated by the number of protons. The number of protons indicates the elemental number, or you could say the atomic number. Yes. The number of protons indicates or dictates the type of element. And it's called the elemental number, or you could say atomic number. These terms will get a little bit similar, so we need to really kind of pay attention to the minute definitions here. The atomic number also kind of gives you an idea of the mass of the element or an atom, okay? The total, I'm going to use this word loosely, the total weight or the mass of an atom is going to be the sum of the total number of protons and the number of neutrons that would be in an atomic nucleus. So I'm going to repeat that. The mass number is calculated by adding the neutrons and the protons in the nucleus. If I add those two things together, I've calculated the what? Mass. If I'm looking at just the protons, I'm looking at the atomic number, the element, right? It tells you calcium, phosphorus, whatever. They're unique. The mass number and the atomic mass are going to be quite similar to one another. What we're going to learn is that some atoms can change the number of neutrons, which would change the what? The mass. And so we can calculate the individual atomic mass of an individual atom if there's some variations about it. Okay, so this is going to be a bit more specific. But notice I have the word up there. You can guesstimate it. Okay? If you can calculate the mass number of the protons and the neutrons, you can guesstimate then the total real mass. And we're not in chemistry. Some of us aren't in chemistry this semester, but it's going to give you a guesstimate. So the mass number and the atomic mass might be pretty much very similar to one another, same type of number. If you look at this layout, our electrons, or excuse me, our elements are distributed on this thing called the periodic table. So this is just a visual cue. And I've got a sample right there in the middle of page 2 to the right. Instead of giving you the whole chart, I'm just going to give you an example of a single element. Okay, so can you see the little helium that I have for you in your handout? Okay. So this is just one of many that I could have just shown you. When we look at, let me come back to that. When we look at the periodic table, there's a lot of information in there. Instead of having to panic, you can actually gain a lot of information from it. And so the value atop the symbol is the atomic number. So on your handout where you see the big 2, draw an arrow or whatever, label that value as the atomic number. So it's element number what? 2. Okay. You also have probably noted that our elements have different symbols. So in this case, He stands for helium. H stands for what? Hydrogen. O stands for oxygen. In our discussion on Tuesday, we learned some of them a little bit tricky. We might think of something that, so we've got usually some Latin origin, so what we think here in America, right, kind of tricks us up a little bit. So, an example like sodium, you might think would be the letter S, but it's actually Na for natrium, which is sodium. So our atomic number gives us what the element is that we're studying. We could also keep it easier for us and use the symbol. And then we can also guesstimate the mass. And is that the element mass or the atomic mass? This would be the elemental mass. This would be the element mass. And if you look at it, we said the atomic number tells us not only what element we're working with, but what does it actually indicate? The number of protons. And what we're going to learn is within a nucleus, usually, but not always, the number of protons and the number of neutrons are what? Okay, the same. So if I have 2 protons, 2 neutrons, the value, the weight, the mass should be about 4. Okay? And so that's why you can kind of guesstimate if you're looking at a single atom. Where we're going is things change. And so we could study a specific atom under specific conditions. But if we're looking at pure textbook elemental properties, usually the same number of protons and neutrons, so you can double up that element number.
And again, the number is the same as elements and mass?
Yes. Yes. Additional questions? Yes. I am going right there. And the electron shell is the area or the orbit at which an electron might be found. So I'm going to hopefully clarify that better for you in just a minute. But it's the region where an electron would be found. We know protons and neutrons are found in the nucleus, and so the shells are the area, kind of the perimeter of where an electron might be kind of bouncing around. Additional questions? Here's an example of helium. Pictorially, right, obviously the protons, neutrons, and electrons are not this big and colorful. They don't tell you their charge, but this is easier to appreciate. Here we can see the nucleus where the protons and neutrons are housed. And then if you look at this first scenario, it looks like a grayed out, like kind of like we used the word gradient, I think, the other day. That's the area at which the electrons would be found, which would be the shell. However, in textbooks, we see it with like a defined, perfect circular area because it's easy for us to see. But the electrons don't have like a railroad track to kind of ride on, okay? They bounce around within this perimeter, within that shell. A visual, I don't know if it's a good one or not, this was in my head, so just envision a backyard at a 3-year-old's birthday party, okay? And you have just served them some chocolate cake and some Mountain Dew and some cotton candy, okay? The kids will be the electrons, okay? And you know they aren't going to stay, they're not going to sit there and walk in a line, right? And say, you need to stay in this yard and go, right? They're going to go all over the yard, right? Electrons kind of do that. It's a little bit more organized than a wild 3-year-old, but there's still a perimeter that they're bouncing around in. Does that visual help a little bit? Electrons are scattering around the nucleus, and we're going to talk about what are some additional criteria to that in just a moment. But the primary thing is that those electrons are moving about, orbiting around the what? Around the nucleus, where we'll find what? Protons and neutrons. Good. We'll keep our appreciation a little bit limited. I'm not undermining that. I'm not saying this is easy, but we're not going like super duper deep. We're going to keep it to 1, 2, 3 orbits or shells, okay, instead of however many they can get up to. So we're going to kind of limit the boundaries for this study to understand how these different atoms and elements interact with one another. Let me back up real quick. I have a spot for you on your handout for you to draw a generic looking atom. So why don't you just draw helium? You can draw, I would draw the far right side so that you can still appreciate that boundary for the electrons. In your image, it should be on the bottom of page 2, a little box to draw. Bottom of page 2. Just draw, you can just put your protons, you can just put plus, or and then just zeros to indicate the neutrons, they are neutral. And then the electrons, you can put them neighboring, or you can put them, actually I put them opposing, one here and then one on the bottom. Alright. So the point is we're just trying to figure out where the electrons go, where the protons and neutrons. If you don't have your handouts, you can just use regular paper. It'd be fine. Okay. Alright, so protons, neutrons, electrons form atoms. What we're going to learn is those electrons, because they are scattering about, they can actually change which nucleus they associate with. Okay? They can actually move over to another atom's and orbit around its nucleus. Okay? So when that happens, we can form an ion. An ion is an atom that has either picked up electrons from somewhere else or thusly given electrons. Let me precede this. A pure atom, before we get into the ionic state, the protons, neutrons, and electrons should be equivalent. So what should the charge be of a pure element? It should be what? It should be 0. Okay? If I have 2 protons and 2 neutrons, they cancel each other out. Or excuse me, 2 protons and 2 electrons, they cancel each other out. And then I have neutrons that have no charge. A pure atom should have a neutral state. Okay? They should be electrically neutral. Atoms should be, right, if they're not reacted yet, they will be electrically neutral. Where we're going is those electrons can actually move from one atom to another. Okay? The electrons have what charge? Negatively charged. So if an atom's neutral and then it gives up an electron, what happens to its charge? It becomes positively charged. It was neutral. You take something negative away from it, it now becomes positively charged.
So, an atom that has the same amount of protons and neutrons is considered a pure atom?
Yes, I mean, yes, yes. Where I'm going is there's another variation. Our neutrons can vary as well. So, short, sweet, I'm just going to say yes. Nothing is simple, right? Okay. So what we need to first understand is if something is neutral and I take away something negative, that atom is now going to no longer be neutral. It's going to be what? Positively charged, because we have the little protons in the nucleus, okay, giving that overall net positive value. The flip side is if something's neutral and it picks up an electron, it's now going to be charged, negatively charged. So there are some variations when the electrons move from one atom to another. They form these things called ions. We're just going to introduce the concepts now. We'll give some better examples in just coming up. Okay? Yes? Yes, something would. And so what happens is, think about magnets. You ever play with magnets? Okay. So if something's neutral, there's no electrical attraction. However, if something becomes charged, whether it's positive or negatively charged, would something be attracted to it? Yes, what? The opposite. And so what we're doing is we're setting ourselves up for bonding, and that's where we're going. But before we can understand bonding, we've got to get through the stuff that you guys just love. So one variation of a pure element is an atom when the number of what changes? Number of electrons. Good. Conversely, we could change, add this to your note. I was forgetting. We did note this, right? It becomes fully charged. Either what? Either negative if it does what with an electron? Gains an electron. It could become fully negatively charged if it gains an electron, or it could be fully positively charged if it gives up, donates, transfers. Some examples, you've heard of calcium. Calcium ion has a +2 charge. So it actually gave up how many? 2 electrons. Sodium has a single positive charge, so it actually just gains 1 little electron. Chloride ion becomes negatively charged, so it gains 1 electron.
So the plus means that it gained it or gained it?
If it becomes, first they're neutral. Okay? So if something becomes positively charged, it lost something negative. Okay. It gave up an electron. And the reverse would be true for something negatively charged. If something's negative, it has gained an electron. Some elements have been man-made and engineered. And if you give me a second, I'll flip back to that periodic chart And these are the ones on the bottom. I don't know all of them, but the ones that are kind of lumped down there in the bottom, they're like, let's create this. So you're correct. And there's room for more discovery and clarification research. We're going to focus up here on the top portion of the chart. So we said a variation of element could be an ion if we change the number of electrons. Ions can be formed if there's a change in the number of electrons. Ions form when there's a difference in the number of electrons. One more time. Ions are formed when there's a change in the number of electrons. We're going with what you said, but it makes a completely different thing. Okay. Alternatively, variations in elements can happen when we change the number of neutrons. If we change the number of neutrons, we don't change the overall charge, but we change the properties of this thing, and it's called an isotope. Isotopes are elements that have a different number of neutrons. If the number of neutrons varies, we have an isotope. It's not a new element because what's remaining constant? And that may be 2, but what defines an element? The number of protons. We have not changed the protons, so we're still looking at an element of the same time, but neutrons have been gained from the environment, and therefore we form an isotope. You've probably heard of this C14, right? You've heard of carbon dating. Anybody had any radioactive treatment for thyroid cancer or some type of thing? What they're utilizing are probably isotopes. Okay, and what our isotopes are elements that have a different number of neutrons. Okay, and if we look at them, many of them can become radioactive. They're just really full of energy. You've heard of the word radioactive, right? You like do it? And I live under a rock, so may not know about the band name Radioactive. But if something's considered to be radioactive, it's a variant of a non-radioactive element. They have the same number of protons, but the number of neutrons will vary. We'll briefly talk about this isotope called C14 in carbon dating at the very end of the semester. It's a tool that researchers utilize to date like fossils and the age of the Earth and those kinds of things. Okay, it's a very accurate tool. Okay, so isotopes have different numbers of isotopes have a different number of neutrons. Ions have different numbers of electrons. Okay, good. We're good for today. All right, and as I mentioned, there's lots of different reasons why you might actually utilize an isotope. Okay, so medical imaging, etc. Okay, so as I mentioned, we'll give some examples at the end of the semester. We had a question earlier. Then, well, what is the electron shell? Okay. And so the electron shell is going to be found in a given orbit. What do you think an orbit is? It's a shape, a boundary around an atomic nucleus. Okay? And it's just a three-dimensional. Keep in mind it's three-dimensional. We have everything in our textbook. It looks flat, but these electrons are in a three-dimensional rotating space, just like that visual I tried to give with the kids in the backyard just going bananas, right? Electrons can do that. My shorthand note for an electron is E with a negative charge, so you can use that in electron. The orbital is just the three-dimensional area where a particular electron may be found. They're not static. They're not sitting there waiting around. They're moving because they are full of energy. The question is, well then, how can we apply that to the electron shell? Okay. Within a given orbit, remember we had our little protons and our neutrons in the nucleus, and then we have our electrons out in the orbit. Okay? The orbitals define the boundaries, define the space, and the shell is just the limit. So the orbit is going to be more the direction, the pattern. The orbit is going to be more the pattern that the electrons take. The shell would be the limited boundary for that orbit. Let me give you a visual up here on the board. I have my protons and my neutrons in the atomic nucleus. I have my energy shell in the dashed lines. And my electrons may orbit, I'm going to show in the blue, like a figure 8 pattern. Can you see the orbit? Or they actually may go in a circular pattern as well. So the orbit is just that area that the electron might be found kind of scattering around it. Within is what? Within a shell.
And that shell is the electron shell?
Yes. The shell, the electron shell, is where the electron orbit happens. So the shell is the boundary. The orbit seeks the area that the electron will be moving about. What's keeping it within its shell is just reactivity. To keep it simple, is the reactivity of those electrons, their attractiveness to the protons, and then the repulsiveness of the other electrons. I mean, yes, it's very complex. So I'm trying to take a very complex thing, make it simple. So you're asking great questions. The rates, I don't know the rates, but faster than you can think about how fast you couldn't count them. The microscopes that can visualize them just give snapshots. I don't think that they can track them. I don't think they can track them. Someone might be able to, but I'm not aware of it. But I can't give you a value. But darn fast, if that's quantitative enough for you. So yeah, they're in constant motion. So I think we're okay on the difference between the shell versus the pattern of the orbit. Kind of got an idea. If we look at the shells, unfortunately there's not just a single shell. The more protons and neutrons that a given atom has, the more energy shells that a given atom needs, because it's going to have more electrons. You can't just jam all these negatively charged electrons in a tiny space. You can't jam 50 3-year-olds, right, hopped up on coke and cake in a 5-foot room, right? Different, right? You've got to get more boundaries, and so the electrons need more shells so they can fill up more orbits. Okay, so it's ordered, right? And the order is they just start from inside out. Okay, so hydrogen and helium just use the first energy shell. If we start adding on to that, we need to go to another energy shell. electrons. If an atom has 3 or more electrons, it's going to have to go to the next energy shell. Okay? The next energy shell can hold numbers 3 through 10. So it can hold up to 8 electrons. So the second energy shell can hold how much? 8 electrons. No more than 8. Yes. Correct. Yes. The third electron shell can also hold 8 electrons. It goes in sequence so. The first shell has to be filled before electrons can occupy the third shell. And then the second shell. And then all of the electrons in the second shell have to be occupying before, if there's additional electrons, would go out into the third orbit, or electron shell.
Can you go over the numbers again?
Yes. The first electron shell can only hold 2. Up to 2. Maximally 2. The second energy shell can hold maximally 8. Okay. As well as the third shell can hold maximally 8. We don't need to go beyond that in this class. That's enough.
So it does it bigger.
Oh, yes. Yes. Very much so.
Do you know what's the biggest?
So we could do, no, I don't, this is where I stop as well, beyond that third electron. And also, if it's complex enough, there are subatomic particles that make this stuff go round, okay? Quarks and just anti-quarks, and I'm like, leave that to the physicists, right, to handle. So we're going with what's well characterized in properties that'll help us understand molecules. And so you could draw your electrons, or excuse me, your atoms like this, what's called the planet model. And so there's 1, 2, 3, 4, and that's the easiest way to draw it. And that's what you'll see it in your textbook. Okay? So what you might want to do over the weekend is just make a number between 1 and 18, excuse me, and then just try to fill the protons, neutrons, and electrons and go in sequence. So that'd be something you could practice drawing different types of atoms in their neutral state. Okay? Going in sequence like that. You could alternatively do what's the cloud. And so this better illustrates those orbits. As I mentioned, the orbits could be circular or spherical, or they could be oblong like this. That's just where electrons are scattered. It'd be the shape of the backyard. All right, so we've already actually addressed this. What we learned is where an electron is going to indicate the amount of potential energy that it can contribute. We have not talked about energy directly yet. We're just kind of getting into the semester. But I think you're okay with the word energy, right? And I think you're okay with the word potential. What does that mean? Possible, okay? This amount of possible energy could liberate to a reaction. So where an electron is going to indicate its potential energy. And that potential energy is dependent upon its energy shell. Okay, so we're still looking at our notes here for our energy shell. Okay, the energy shell is going to indicate, as the name implies, the amount of potential energy for an electron in that given area. You go back to your list that you had earlier. First, second, third energy shells. The first shell is going to have how much? A lot or a little? Little. Second one's going to have more. Third is going to have even more. Okay? So the further an electron gets away from the nucleus, the more reactive it is. The more potential energy that it has. It has a lot of electrons in it. So the further an electron is away from the nucleus, the more potential energy it possesses. Now, to add some further technicalities to this, we're okay with first shell, second shell, third shell, and we could keep going on with that. Okay? From that, we can use this thing called the valence shell. So we're still on page 3 of your handout. The valence shell, I don't have the word electron up here, but in your notes it says valence shell. The valence shell refers to that outermost shell, whether it's the third, second, or first. The valence shell is just the last shell of that particular atom. So I could say the outermost shell, or I could say the what? The valence shell.
Does that have the highest amount of potential energy?
It depends on the number of electrons in it. Okay? And so that leads me right to the second point. Within the valence shell, we have the valence what? Electrons. Okay? So what we know is not all shells have the same amount of electrons, so the number of electrons in the valence shell, say if we're looking in the third orbit, I may have 1 valence electron, or I may have how many? 8. Okay? So that's going to play into there. Furthermore, okay, so obviously the more electrons, the more energy it has. Where it might get even more confusing is we're going to use this term called reactivity. Okay? Reactivity. So, under your notes where it talks about valence electrons, we know that those are electrons in the outermost shell for that. Those are the ones that are going to do what? They're going to do what? Interact. They're going to give energy. They're going to interact with other atoms. And those are the ones doing the reactive work.
So the valence shell is actually the outer limit.
Yes, the outermost. And the reason we use valence is because we saw all the elements on the chart. I mean, you're going to start saying how many are there? I mean, instead of just applying a number to it, you could just say the valence, the reactive shell. So the outermost shell, the valence shell, we know that the number of electrons varies. But because it is the outermost reactive shell, we have to take into consideration the number of electrons in there. If that valence shell is full, so let's say we're looking at the third shell and we have 8 electrons. If it's full, it is considered to be stable, not reactive, not very reactive. Let me repeat that. If the outermost valence shell is full, so let's say it holds 8 electrons and there's 8 electrons there, that atom is considered to be stable, or that valence shell is stable, not so reactive. Flip side, if it's not full, it's more reactive. And the more empty it is, the more reactive it is. Because it wants to be where? The fewer electrons, yes, the more reactive it is. Because in a biological system, really, if atoms had a preference and a thought, they don't want to be reactive, they want to be stable. The only way to get stable is to react, right? So let's make that shell stable, okay? Does that make some? You're not crying yet, so that's good. All right, so we know about the valence electrons. We said those are the electrons in the outermost shell. The valence shell is most stable when it's full, more reactive when it's more empty. Okay. We already identified this, but we can practice again on page 3 of your handout. So, energy shell number 1 can hold up to 2. Check out my orbits. Check out my animation skills. Oh, hold on. Put you on suspense. Second shell can hold up to 8. Third can hold up to 8. And then they can orbit within that shell. Right? Sorry. Played out.
So the second shell also orbits within the first shell, and the third shell
They
orbits
orbit around that nucleus. They all center around that nucleus, yes. 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 Yeah. Does that help? Did that awesome animation help you with the shell and the orbit and the boundaries? And so the whole point is, where we're going is once we understand a single atom, we can understand how it can react with other atoms to form these things that we're going to study called molecules that you guys did on your little handout for homework, which we'll go over in just a minute. Here's another visual. In this image, we can see the 3 electron shells, energy shells, partially filled, but in this image, the purple is indicating the presence of an electron. The empty white indicates the absence, so it could be reactive. It could gain up to how many? 8. In this shell, it can actually gain 2. This sulfur. Its valence shell has only 6 in it, so it could gain 2 electrons to become stable. Let's count them up. 1, first shell, I only count 1, 2. Okay. Second shell, if I see a third shell, there better be how many here? 1, 2, 3, 4, 5, 6, 7, 8. There's more than 8, so I need to go to the third shell. Just because there's a third shell doesn't imply that there's going to automatically be 8. There may be just 1. In this case, we have 1, 2, 3, 4, 5, 6. So it has empty seats for how many? 2. So it could gain 2.
and then everything's stable.
Yes. And it would have a charge of, it's neutral itself. Protons, neutrons, electrons match. But it could gain 2 electrons, so it would have a charge of, electrons have what charge? Negative, and I give it 2, so it would have a charge of positive.
I don't know.
If I have a bank account of $0, or I have a neutral atom, right? And then gaining an electron, that's like taking out money. Okay? If I take out if I give 1 electron, my bank account is now nothing. I took out I gave a negative. Right? And if I got another electron to it, my value is now. So something's neutral, you give it 2 negative components, the value negative 2, and we would call it an gained electron, we would call it an ion. Okay, good. So, in summary, and that point of confusion is just because a particular energy shell is attained, it doesn't mean it's spontaneously just full. It may have 1, 2, or if we're looking at the second, it may have up to 8. But if it has 6, it has the reactivity of, it can gain up to 2 to become stable, but it would then have a, what type of charge? Negative charge. So that state is stable, although it's negative. So maybe where you might be confused is don't think of necessarily everything for being stable yet neutral. I said don't do that. Don't do that. Don't make that presumption. Yes. All right. We have an idea about electrons. They're moving about. They're given the reactivity. They have to go in this ordered shell reaction. Okay? Now what we want to do is combine different atoms to form different compounds, and more specifically different types of molecules, so we can understand nutrients, sugars, proteins, and etc. So, one type of bond that we're going to see, and if you didn't get into D12, you may not, I guess you do have the back of this, but if you didn't get the rest of the chapter, remember I said you need to get the rest of chapter 2 handout, so if you don't have the rest of those, I'll have you, you can just take traditional notes. But the different important types of bonds that we're going to study, I have listed for you in a simple table. This is not at all of the different types of bonds. These are some of the really important ones that you'll use. Okay? So we're not going to talk about everything. Okay, so this is not an all-inclusive list of all the different types of bonds that are available to atoms out there. Okay? One important bond that we're going to study is called a covalent bond. In a covalent bond, you have two atoms, and they actually share electrons. Covalent bonds, the word I want you to highlight, circle, capitalize, whatever, is the electrons are what? Shared. Electrons are shared. Valence, notice it's the valence electrons, are shared. Why? So the two atoms become, the result is they are bound together, and the whole point we said atoms want to reach stability. They become more stable. In a covalent bond, two atoms will share their valence electrons, and they should become more, the resulting molecule will become more, what? Stable. Okay, the whole point is, in our covalent bonds, right, some importance, is it, as I mentioned, it forms our different types of molecules. The number of covalent bonds varies. You may have a single covalent bond, a double covalent bond, or a triple covalent bond. What do you think happens as we increase the number of covalent bonding? More stable, and it's really, really strong. It's going to be very difficult to break that bond. Some of our strongest bonds. Those atoms that are bound covalently, very difficult to, they won't spontaneously break. Some chemical reaction is going to have to break them. And something else is going to be added to it. So they're really strong, really stable. Have you ever shared something? Anybody have a sibling? Yeah. Okay. So if you have a sibling, you ever shared? Sharing is like implied, right? Was the sharing always equivalent? Okay. So sometimes things work, and the sharing is equivalent, and sometimes the sharing is not equivalent. Okay? So if we're sharing electrons to reach stability, if the electrons are shared equally, the electrons orbit around the nuclei of the two atoms the same amount of time, so that both atoms have what type of charge? electron sharing is equivalent. Those types of bonds are called non-polar covalent bonds. Okay, so let's describe this. In your you got a I think it's like you got to bump down to B, 1B. In your non-polar covalent bonds, the electrons are shared equivalently between both atoms at which they're orbiting. And the sharing is equal. Yes. In a nonpolar covalent bond, the electrons orbit both atoms at the same rate so that the resulting molecule is neutral. The electrons are shared equivalently, equally. Those are called nonpolar. So by process of elimination, if the sharing is not equivalent, that covalent bond is probably called polar. A polar covalent bond is where electrons are shared, but electrons may spend more time around a single atom, so that area becomes a little bit more what charge? Negatively charged. And the other atom gets less of the electron, so it becomes a little bit more positively charged. And so within that molecule, part of it is positive, the other part of it is negative. Okay? And so we could say the molecule is polar. Which, you've probably used that word before. If you think about the earth poles, the opposites, within that molecule they have opposite charges. One end is positive, the other end is negatively charged. As a result of unequal sharing, unequal distribution of the electrons spending time. Yes?
Anything below the equator. Anyway, you know, it goes to above the equator, the water. Below the equator,
Yeah. It's because of the charge in the poles of the Earth. So certainly, you can appreciate how charges affect the Earth as a whole. Something silly like what you might think about toilet flushing, but then we can also zoom down to the atomic and molecular level. Those charges are going to influence the pool of how these molecules interact with one another. Good.
Question.
Yes.
All of this sharing and bonding is happening in between the shells, right?
Yes. And most specifically, if we're forming a molecule, it's going to be those valence shells.
Molecule that forms in the valence.
Yes, it's the valence shell where the sharing happens, that outermost reactive part. Okay. Here's an example of the most important polar molecule. So under your polar covalent bonds, we're going to use this term over and over to describe water. Water is described as a polar molecule, so you must know it has what? Unequal sharing, so it's not neutral. Part of it is part of it's negative, part of it's positive. We don't really know the structure of, we didn't go through the atomic structure of oxygen or hydrogen. However, what happens is in water, oxygen hogs the electrons, and so oxygen becomes partially what? Negatively charged, and the hydrogens become positively charged. We're setting ourselves up for a whole other type of reaction now. Polar molecules can then interact with other types of what? Other polar molecules. You okay if I talk about a polar covalent bond? Electrons are shared. Here we can presume it in this image. Hydrogen, oxygen, and hydrogen are sharing electrons, but the sharing is not the same. So that oxygen becomes more negatively charged, and the hydrogens become a little bit more positively charged. You might want to note that it is a partial, not a full charge. Not completely, it's just a little bit. Because you remember our electrons are bouncing around, so sometimes they're around hydrogen, sometimes they're around oxygen, so it doesn't create a full charge like in what? Ion. Remember we thought ion would be either fully positive.
That was like an hour ago.
So our ions have a full charge. Our polar covalent bonds would have partial positive or partial negative charge. Okay. All right. So nobody's crying yet, so we're going to keep on, keeping on. We already talked a little bit about ions. We know what they are. And once an ion is formed, we can form an ionic bond. Because we know that if something has a full charge, it could interact with something that is what? If something, say, positively charged, it could interact with something that's oppositely charged. Okay? So we know about an ion. When an ion is formed, we learned that there was a full transfer. So notice that there is no what? It's given up, right? It's not no longer what? There's no sharing. There's no right. So an ion is a result of it just full on takes an electron or full on gives an electron. Okay? So it is either fully positively or fully negatively charged. That's an ion. Sodium, potassium, whatever. The follow-up to that is, well, if something is fully positively or fully negatively charged, it then itself can bond with something. So we first got to form the ion, but once the ion is formed, it can react with something else. And if we have two ions, full charged particles, bonding together, we can do an ionic bond. I'll come back to the description on an ionic bond. Let me finish with your list in just a second. The proper terms for those ions when they have a full full positive or a full negative charge, we could call them cations or anions. Anion, which one do you think that means? Negatively charged. An anion is a negatively charged atom. It's a negative, so it must have got an extra electron. It was neutral, got an extra electron, and became negative. An anion is a negatively charged atom. It's gained however many electrons. Okay, 1, 2. I don't think it will get above 2 in some of our examples. Conversely, a cation must be positively charged. So what did it do with its? Lost, transferred, donated its electrons. An example of an anion that you would be familiar with is chloride. You would write that as Cl negative. We've got a lot of examples of cations. Potassium ion would be written as K+. Calcium ion you could write as Ca2+. You could write sodium Na+. Those are, if I were to read that, it would be, the charge would say, I would use the word ion. Okay, sodium ion, calcium ion. If I see that full charge on there. Now, the question is, if we know where they're formed, if we understand the creation of an ion, and so for example, great example, is sodium. If you look at its valence shell, it's pretty empty. It has how many electrons in its valence shell? 1. So in theory, it could take up 7, but that's a lot of work, so it's probably easier to do what? Donate that electron out, and now it goes to which energy shell? Second, and becomes more stable. However, when it gives up that electron, it now has a charge of, it gave up one electron, so now it has a charge of single positive. Its little buddy in nature is chlorine. Chlorine, look at its valence shell. It has how many electrons in its valence shell? 7. So to make it stable, it only needs to bind with 1. And it wouldn't make sense to go out and give up 7 electrons, but it's easier to give up, or excuse me, accept 1. Okay? And so they're made for each other. Okay? When sodium transfers its electron to chlorine, we now form positively charged sodium ion, and chloride becomes an ion with what charge? Negative 1. Okay? And now, if you look at them, their valence shells are satisfied. They're more what? Stable. But now we call them ions. Now they have full charges, and now what can they do? Once the ion is formed, they can bond to one another. And so that's called an ionic bond. An ionic bond is a bond, and why don't you clarify on your notes, it's an electrical attraction between an anion and a cation. It's electrical attraction. Between an anion and a cation. So if I were to bond sodium ion and chloride ion together, I would form a what molecule? Sodium and chloride bound together makes and what's the proper name for it? Sodium chloride, or you could say salt in this case. All right. And the resulting molecule would be, as a result of the ionic bond, you've now formed an ionic compound, sodium chloride, for example. The bond is the reaction, the compound is the resulting compound. And pictorially, the example that we used was sodium chloride. A compound, sodium chloride, is a result of an ionic bonding between sodium ions and chloride ions. This new compound. I have about 3 minutes, so I'm going to use them. So we can go ahead and talk about the last type of bond, which is called a hydrogen bond. It's a very similar type of bond. And it's a little bit more specific in that it's going to be a covalent bond. And so we're okay with that. So that means it's going to do what? The hydrogen is covalent, sharing electrons with some other atom. Okay? So we're getting a little more specific. We're looking at hydrogen being covalently bound to something else. If you remember, for example, in water was a polar molecule, right? So when hydrogen, because of the way it's built, is bound with something else, it usually creates a polar molecule. And because, do you remember what partial charge hydrogen has when it's covalently bound, say like in water? It becomes a little more within this water molecule, the hydrogen ion becomes a little bit more positive because its electrons spend more time around oxygen. So this right here, this molecule, because it's partially charged, the hydrogen component can form a hydrogen bond with something that has what type of charge? If it's positive, it can form oppositely charged something. The hydrogen bonds are oftentimes illustrated with just little dots. illustrating this weak electrical attraction. So on your hydrogen bonds, clarify that this is a weak electrical attraction of hydrogen in a compound to something else that has what? A positive, a negative charge, excuse me. The hydrogen is positive, so it would attract to something negative. What I want you to add to your notes is hydrogen bonds are really weak. But don't misinterpret that as not useful. They're critical to molecular formation. What I'm going to do is go ahead and conclude our discussion here.